another video. Yes, more mathematics. In this video, we're going to be talking about functions and where they increasing, decreasing, and constant. We'd like to describe, given a graph of a function, where this function is increasing, decreasing, or constant. So, we're going to talk about that. Now, to get started, we're going to look at some definitions here to help us out. And then we're going to look at some examples. So here we go. First of all, up there at the top is definition. Excuse me. We're going to get our setup. Our setup is that let's consider an interval I right there to be some open interval. So an interval which does not contain the endpoints. Something like the interval A, comma, B. Something like that, where A and B are real numbers. So it's some open interval for which we're going to call I, and we're going to assume some function f of x is defined on this interval. And also, x1 and x2 are actually part of the interval I, assuming that x1 is the smaller of the two x values. So in other words, we got these two values, x1 and x2. We're going to assume they're real, and we're going to assume that both of these x values belong to the interval I, and the interval I is some open interval, for instance, a to b. Okay, that's our setup. We got those things going on. So, as you could probably already see in the screen here, if that's our setup, then we say that the function f of x is increasing on that interval if we have that the value of the function at x1 is less than the value of the function at x2, and of course this follows for all x1 and x2 in the interval I. So you see the picture here below. We got the x1 down there, we got the x2 right there, and obviously x1 is smaller than x2, it's to the left of x2. And you can see at x1, the value of the function is something. There's the ordered pair corresponding. And then at x2, the value of the function is up there. Ordered pair somewhere right there. The value of the function f of x2 is bigger than the value of the function f of x1. What that really means is, as you move left to right on this interval, every single time you move farther to the right, your function is getting bigger. Hence, you see us, we're moving up the hill, if you will, reading left to right. In the x direction, the function is getting bigger. That's what it means to be increasing. Likewise, what it means to be decreasing, zoom, is basically the opposite of when it's increasing. That is, still assume x1 is still left of x2. Then the value at f of x1 should be bigger than the value at f of x2 for all x1 and x2 in the interval I. And all that really means is as we move left to right in the x direction, our function is getting smaller, decreasing. That's what it means. And finally, what about if a function is constant? The word constant means it doesn't change. And as we see in the graph here, the output is always something, whatever it may be. It's not changing. Hence, you see the horizontal line. But by definition, still assuming we got any x1 and x2 values in our interval I, x1 to the left of x2, then it should follow that every single value of the function in that interval is the same. Hence, the outputs f of x1 and f of x2 are the same values throughout the interval. So we got increasing function, decreasing function, constant function, all on some open intervals. Those are the definitions. So now we got a couple of examples to consider to help us understand these ideas a little bit better. I'm just going to switch colors real quick. How about purple? Purple. All right, here is an example. You are given the graph of some function f of x. It looks a little weirded out down there. It's doing a bunch of different things, but that's on purpose because we want to describe all these different behaviors. So, given this graph, let's answer all the following questions. Let's find these different intervals that we're asked to find, and we're going to use interval notation. First question, what is the domain of the function? And as we can see, the function is always defined for every value of x. From left to right, the function is defined. So the domain, all real numbers, x. How about the range? Well, the range values, of course, are all the output values that result from the domain values. And that means we're going to be looking bottom to up. So as we move up, we can see that the function down here in the bottom right, it goes down to negative infinity. So we can keep going down, down, down. And then we move up, we move up, we move up. And then over here, we can see it also goes to infinity with all the values in between. Hence, the range is all real numbers x. So that isn't anything new. That's just to reinforce the ideas of domain and range. But now for the new stuff, increasing, decreasing, constant. Well, increasing. As we move left to right in the x direction, where are my output values getting bigger? So we could start way down here in the far left, and as we can see, as we move left to right, we're going down, right? Our function values are getting smaller, so it's not decreasing there. But it does start to increase here as we change from going down the hill to going up the hill. So right on this little shaded region on the quadrant 2 here, we're getting bigger as we move left to right in the x direction. And then down the hill, not increasing, staying flat, not increasing. But then at 2 again, we start going up a hill. And then we'll keep going up the hill to 3. And that's it. That's where it's increasing. So how do we write that using interval notation? Remember, to describe increasing, decreasing, and constant locations of a function, we always use open intervals. The reason for that is I'd have to use a little bit of calculus to really describe it, but kind of think about like at this number -4 here for x, we're changing from going down the hill to going up the hill. And so at -4, we're kind of neither increasing or decreasing. That's an informal way of thinking about it. But regardless, we got to write the open interval. So here we saw that we were increasing starting at -4, not including open interval. And then we do this all the way up to -3, describing always from left to right in the x direction, which x values is true for. So we could say like x belongs to that interval if we want. But it also belongs to the interval 2 to 3, also open. So we put the little union in between, if you recall. It's coming from this interval or this interval, that is the interval from -4 to -3, increasing. It's also increasing on the open interval 2 to 3. So I'll erase all my little marks we just made. Now where is it decreasing? We're going down the hill from left to right. As we move to left to right, so we're going down the hill in that region there. Also going down the hill in that region there. And finally, starting at 3, we go down the hill forever after. So 3 different intervals where we're going down the hill as we move from left to right. So the x's here should be coming from, well, all the way down from negative infinity, and then we're going to stop going downhill at -4 for the x values. We start going down the hill again at x is -3, down the hill all the way to x is -1, and then finally we go down the hill starting at 3 again forever after. This is where the function is decreasing. Finally, where are we constant? Constant just means we're not changing outputs. We're on the horizontal line, so we can see there's that part of the graph where we are not changing values, the same value over and over and over again. In particular, the value -2 is an output. And so on that interval, starts doing this at x is -1 and stops doing it at x is 2. So we could say that this function is constant from x is -1 to x is 2. And there you have it. There's an example of describing intervals of x's for which a function is increasing, decreasing, or constant. We'll do one more. Here's another one. This one's all pieced together. It's got some jumps and whatnot, but now this is some function. Maybe I'll use another color for this one. How about orange? All right, this function this time is y is g of x. Not that it really matters what we call it, but that's the name of the function. And we're going to do the same thing. We're going to describe all the same things that we did in the previous problem. Then starting with the domain. So the domain, as we move left to right, we're going to look for places, some x locations for which there is no output value. So as I move left to right, we're on the graph, we're doing all okay. And then all of a sudden there's this problem. There's no output at -3. It switches rules there, and then it switches to this line, and where it switches rules at -3, there is no output. So hence, x equals -3 is not part of this domain. So you got to keep that in mind. And then as we move from left to right, we keep going. It does jump again at -1 to this other horizontal line here. But as we can see, at x is -1, there is a value right up there. So see the dot, that means there is an output. The output at -1 is +3. So then that's included. So x equals -3 is not in the domain. And as we move from -1 and continuing on, we get to this place x is 2, for which it switches rules again. And as we can see at x is 2, there is no output value. Hence, x equals 2 is not part of this domain either. After that, we continue on our way. Everything is defined. So the domain is going to include all values of x that are not -3 and not 2 for those reasons. Hence, the domain should be the interval of x values starting from -infinity all the way up to -3. -3 is not part of the domain, so we jump over it. And then -3 all the way up to 2, we're good. And then 2 is not included, so we're going to jump over that again and move on to infinity. There's our domain. How about the range? From bottom to up. So you can see the arrows, that means we're going down to -infinity. So definitely we're going to be starting at -infinity in the output direction. And then as we move up, we move up, we move up, there is this spot right here. Is, oh no, there's no output of -3. But actually there is, it's over there on that graph. So we're all good. We keep moving up, moving up. And then there's this problem right there at the output of -2, but there is an output of -2 over there on the graph. So we're still all good. Keep moving up, keep moving up, keep moving up. See right there, there is no output on this part at -3, but the output of 1 does occur over there on the right. Keep on moving up. Take on the value of 2 in all these locations. Keep on moving up. And then we finally stop in the output direction at 3. So actually, this function is defined all the way down there from -infinity all the way up to 3. And 3 here, we actually going to put the bracket because 3 is included as an output in the range. Okay. Now for the increasing, decreasing, constant. Increasing, let's look at the graph, move left to right. We're increasing on that part. We're increasing on that part, getting bigger as we move left to right. And we're increasing on that part using the open intervals. So hence, we're going to be increasing from negative infinity all the way up to negative 4, not included. Switch to the next interval, which is starting at negative 3 and going up to negative 1. Still open, always open for increasing, decreasing, constant. And then finally on the interval starting at x is 2 and then stopping at 3. So there's our interval of increasing values of the function. How about decreasing? Decreasing, we're going down on that piece and we're going down on that piece. So again, using x values moving left to right, we're starting to decrease starting at x is negative 4. We stop decreasing at x is negative 3. And then we start decreasing again at x is positive 3. And then it decreases forever after that. Finally, where is function g of x constant? Well, that's where it is horizontal on the graph. It's not changing output. So the location for which that happens is this piece right there. It starts being constant at x is negative 1, and it continues to be constant until x is positive 2. And there you have it. There are some examples of describing functions where they're increasing, decreasing, or constant. So I hope that that video helped you a little bit. And of course, it's time to be done with the video. So stay tuned for more videos or watch the other ones that are already there. They're all so informative and interesting and beautiful. And they all got beats. Math and beats. I'm out. Later.